let's look at this implicit curve, and we want to determine the linear approximation to this curve at the point 1, 2. It's important to remember that this is an implicit curve, x cubed plus 2xy plus y squared equals 9. And that is implicit because we have a mixture of x's and y's, and we have not solved explicitly for one of the variables. Now, this is an interesting curve that I have already put into Desmos for you, and I've put the graph here. So you can see it's not a function. It's kind of a crazy curve. And we're interested in finding the linear approximation to this curve at the point given. So first off, it's important to remember what a linear approximation is. Remember, a linear approximation is just a tangent line equation. So we essentially just need to write the equation for the tangent line. Now, if you go ahead and sketch in what the tangent line might look like, remember it's going to be the line that is just going to touch the curve at the point 2, 1. So if you can visualize this, here's our point of tangency, 2, 1, and then this tangent line, that is our linear approximation. We're just trying to write the equation for that tangent line. So to write the equation for any line, we know that we need to have a slope. To find the slope, we need to compute the derivative of this function with respect to x. And because this is an implicit equation, we're going to take the derivative of both sides with respect to x, so we're using implicit differentiation. Now the derivative of x cubed will just be 3x squared. However, when we compute the derivative of 2xy, we need to recognize that this is a product. We really have 2x times y, so we have to use the product rule here. So for the product rule, we'll take the first factor, which is 2x, and multiply that by the derivative of y with respect to x, so that's dy dx, plus the second factor, which is y, multiplied by the derivative of 2x, which is just 2. So that's our product rule in blue. The derivative of y squared will just be 2y times dy over dx, and the derivative of 9, a constant, is just 0. So looking at what we have now, we have two terms that contain the dy dx, so we're going to keep those terms on the left side, and we'll go ahead and subtract the other terms to the other side. So 2x dy dx plus 2y dy dx will be equal to negative 3x squared minus this term that says y times 2, I'm going to reorder as 2y. So then we can factor out a dy dx, and then of course we'll finish this by dividing. So our final answer for our derivative, dy dx, will be negative 3x squared minus 2y divided by 2x plus 2y. That is our general derivative. Now we want to find the slope specifically at the point 1, 2. One way to notate that, you can draw your vertical line and put your coordinate at the bottom of the vertical line, indicating that essentially you're just going to plug in 1 for x and then substitute 2 for y. So we'll go ahead and do our substitution and then calculate the slope at this point. This comes to negative 7 divided by 6. So remember, that is the slope of the tangent line. We're getting a negative slope. If you look back up the red line that I drew in for my tangent line, you can see that that looks like it's a negative slope. So we have a slope of negative 7/6. So to finish this off and write the equation of the tangent line, we can use either slope-intercept form or point-slope form. Totally up to you. I always prefer point-slope form if I know the point and the slope, which I do. So my point is 1, 2, and we just found that the slope of the line is negative 7 divided by 6. So the equation for our line would be y minus 2 is equal to negative 7/6 times the quantity x minus 1. This is totally acceptable. That's a great tangent line equation. If you don't like it, of course, in that form, we can add the 2 to the right-hand side and leave this as negative 7/6 times x minus 1 plus 2. You can even change the y out and replace it with L of x, which is often what they'll do in a textbook when they're asking you to write a linear approximation. They'll use L to represent the linear approximation. So these are both great answers. And you could even distribute the -7/6 in if you wanted to get a line written in slope-intercept form.